Okay, we're working on properties of logarithms. We're going to work through some examples, and in these the directions are write each expression as a sum or difference of logarithms. Express powers as factors. And that means that we're going to be using these properties in this direction. We're going to be going from something that looks like the left side of one of these equations to something that looks like the right side. The ln of, and remember that is a logarithm, it's a natural logarithm, the ln of xy over z. So according to property 2 here, whenever we have a log of something over something else, we can rewrite that as the log of the thing on top minus the log of the thing on the bottom. So this turns into ln of xy minus ln of z. See something else we can do now? Where we have ln of xy, we can turn that into ln of x plus ln of y. And then we've still got minus ln of z. And now we're done. We've broken this apart as much as we can into a sum or difference of individual logarithms. So there are certain situations where something like this, made up of individual separate logarithms added or subtracted together, is a lot easier to work with than something like this. Let's try another example. Start with log to the base 2 of x to the 4th power. Now this expression fits the pattern of one of these three things here. Do you see which one? Right, the third one. Log to the base 2 of x to the 4th power is equal to 4 times log to the base 2 of x. The log of something to a power is equal to the power times the log of the something. How about this one? Log to the base 5 of 8y. Which of these three does that fit? The first one. So that's equal to the base 5 log of 8 plus the base 5 log of y. How about this? The ln of e cubed x. Well, this is another one where we have the log of two things multiplied together. So we can break this up into the ln of e to the 3 power plus the ln of x. And now the ln of e to the 3 power is just 3. Because remember, ln of e to the anything is that thing. The ln, the natural logarithm function, undoes what the e exponential function does. So ln of e to the 3 is just 3. So we've got 3 plus ln of x. How about this one? The log, and since there's no little subscript, that means it's the common log, the base 10 log, of the square root of 1 over y. Now, first of all, when you have the square root of something, you could write that as a 1/2 power. Taking the square root of 1 over y is the same as taking 1 over y to the 1/2 power. Or we could say it's 1 over y to the 1/2 would be y to the negative 1/2. So probably the easiest thing to do would be to take that and use this power rule and say, okay, that's equal to negative 1/2 times the log of y. But if we kept it like this, log of 1 over y to the 1/2 power, that third property says that that's equal to 1/2 times the log of 1 over y. And then for the log of 1 over y, we could break that up into the log of 1 minus the log of y by property 2. And then the log of 1 is 0. So 0 minus the log of y would just be negative log of y. And then 1/2 times negative log of y would be negative 1/2 log y. How about this? ln of e to the 6th over 10. Which property is going on here? The second one. We have the log of a quotient, and so that's equivalent to the ln of e to the sixth minus the ln of 10. And then do you remember what we can do with ln of e to the sixth? All right, it's just equal to 6. So we end up with 6 minus the natural logarithm of 10. Now we're going to be going the other direction. Here the instructions say write each expression as a single logarithm. So instead of two separate logarithms added or subtracted, we're going to put it together so it's just the whole thing is the log of some maybe complicated expression. So the base 4 log of 7 minus the base 4 log of x. Do you see which equation has a right-hand side that looks like what's going on here? Yeah, it's the second one, the one with subtraction. And the subtraction is going to turn into just one logarithm of a quotient. So this is equal to the base 4 logarithm of 7 over x. What about 2 times the base 10 log of p plus the base 10 log of q? Now, I might as well just write these as plain old log, because log to the base 10 is the common log, what we usually mean when we just write log without a little number down here. And then 2 times the log of p, we can write that as the log of p to the 2 power. So now we got log of p squared plus log of q. And by using that first property, we can combine those into the log of p squared times q. How about this one? 1/2 ln x minus ln x plus 4. So first, do you see what we can do with the 1/2 ln x? By that third property, it's equal to the ln of x to the 1/2 power. Now do you see what we can do when we have ln of one thing minus ln of something else? We can write it as ln of x to the 1/2 power over x plus 4. So that's our final answer, or if you'd rather write it instead of x to the 1/2, that's equivalent to the square root of x, so we could say that this is ln of the square root of x over x plus 4. How about this? 5 times, in brackets, ln of x plus ln of 4x minus 1 minus ln of y. Okay, first let's take care of what's going on inside the brackets. This is addition. We can turn addition of two separate logarithms into the log of a product, like this. ln of x times 4x minus 1. And I went ahead and multiplied that through and got 4x squared minus x. Now we've got 5 times the ln of something, and that's equivalent to the ln of the something to the 5 power. So now we got ln of 4x squared minus x to the 5th power minus ln of y. And now property number 2 says that the log of one thing minus the log of another thing, or in this case the natural log of one thing minus the natural log of another thing, is equal to the natural log of the first thing divided by the second thing. So now we are done. We've expressed this as just one logarithm. It's the natural logarithm of 4x squared minus x to the 5th power over y. Now, last set of properties or rules or formulas, and the book starts with these. I didn't tell you about these until after I told you about those other properties, because it's those other properties that explain why these work. But this change of base formula lets you change a logarithm to one base into something involving a different base. And where this is really handy is your calculator has buttons on it to give you a common logarithm or a natural logarithm. But what if you wanted some other kind of logarithm? this tells you how you can find that on a calculator. You can find a log to any base of a number just by taking the common logarithm of that number and dividing by the common log of whatever the original base was. Or you can use natural logarithms. Take the ln of the number divided by the ln of the original base. So for example, let's see how you would use a calculator to evaluate something like the base 9 logarithm of 43. So I could put it in as the log of 43 divided by the log of 9. And I get 1.711795942. So that's the base 9 logarithm of 43. And remember, that means that that's the power you have to raise 9 to get 43. 9 to the 1.711795942 power is 43. We could have also done it by taking the ln, the natural logarithm of 43, divided by the natural logarithm of 9. ln of 43 divided by ln of 9 is also 1.711795942. So a couple more examples. The base 5 logarithm of 37. Take the log of 37 divided by the log of 5. And we get 2.24 and so on. The base 11 logarithm of 8. Take the log of 8 divided by the log of 11. And we get 0.867 and so on. Now let me explain why this works. Why does this work to get us the base 9 logarithm of 43? Well, let me use x to stand for that number, the base 9 log of 43. If we write that in exponential form, it would say that 9 to the x power is 43. Remember, the base 9 logarithm of 43 means the power you have to raise 9 to get 43. So take this equation and take logarithms of both sides. If 9x equals 43, that means that the log of 9x has to equal the log of 43. Now that third property from our list of properties says that the log of something to a power is equal to the power times the log of the something. So now we have x times the log of 9 equals the log of 43. Now when you have x times another number and you want just plain old x, how do you get x by itself on one side of the equation? Divide by the number it's being multiplied by. So here we divide both sides of the equation by the log of 9, and x is the log of 43 divided by the log of 9. So that shows why the log base 9 of 43 is equal to the common log of 43 divided by the common log of 9. And in this step where we took the log of both sides, it would work out pretty much the same if I had taken the natural log, the ln of both sides, or really any base logarithm of both sides.